Okay, welcome to our talk. Safari holds still for 9 minutes. So this is very interesting how it happened this morning because we had the privilege escalation on, on iOS and Mac. We had the sandbox escape. And now we also saw how to find even the implants and the viruses. And what's missing now from the full chain? The render remote code execution. So there we go. Full training of full chain exploit. My name is Javier Jimenez, and here's my colleague Vignesh Rao, sorry. We are vulnerability researchers at Exodus, and we've done a lot of dry runs. We started with 1.5 then we went down to 50 minutes, and then they told us to cut it to 40 minutes. We still have 80 slides, 80 plus slides, and some animations. So without further ado, let's go into the agenda. There is one thing I want you to take away from here, and there are 4 big blocks. There's one big block on fuzzing, where you can get some takeaways in there, in terms of how to instrument, how to attack JavaScript engines, and so on and so forth, and how to not reinvent the wheel. Then there are 2 bugs, which are important for our research, for our remote code execution. And then another bug that doesn't have anything to do with it, but the thing is that we discovered something. There was a breakthrough with that gave us a really good primitive in order to get the remote code execution. Cool, so a little bit of an introduction to JavaScriptCore. JavaScriptCore is the JavaScript engine that runs within Webkit. Webkit is the web browser engine that runs within Safari. So when JavaScript runs in your Safari, what is running is JavaScriptCore under the hood. I'm going to ask you to make a mental effort of remembering what a JS value is. Okay? A JS value in JavaScriptCore is an 8 bytes value that points to anything that is exposed in JavaScript. And this can be JavaScript objects, or doubles, or integers. So we're going to see that. So the objects will be a pointer. And a pointer internally in JavaScriptCore will be represented as follows. The upper 16-bit will always be 0, and the rest will be the address in memory. So if we see this, we think JS value, 8 bytes, upper 16 bits are 0, so this is a pointer for me and for JavaScriptCore. Then we have that the doubles, which is numbers with decimals, will be represented as follows. It will have the upper 16-bit from 0002 to FFFFC. Okay? So if you see in memory in value those 8 bytes starting with those values, we think a double value, and JavaScriptCore is going to think the same. And finally, we have integers. So the same applies. Upper 16 values FFFE, then followed by zeros, and then the integer value is encoded here. Cool, so let's see that in a little bit more detail, because this is very important for the bug number 2 and for the success of our exploit. So an object looks like this in JavaScript. I don't know if you can see it from the back, but imagine an object that has properties x and y, and x is 1 and y is 2. And then we have that in JavaScriptCore, all objects are backed by a C++ class, which is called JS object. So a JS value points to a pointer in memory, which is a JS object. Then we have what I just said, and then doubles. One thing about doubles is that they are encoded in IEEE 754. If you want to understand the format of IEEE 754, be my guest. I still don't understand it fully. Then we have something very important. And it's that doubles, to encode doubles, in the IEEE 754, we could have a double starting with zeros as well. But here, in JavaScriptCore, in order to know that that's a double, they add 2 to the power of 49, which is basically adding 0002 all zeros, so that JavaScriptCore knows that that's a double. This is called NaN boxing. Okay, remember this. This is called NaN boxing, and this is how JavaScriptCore boxes the doubles. And another mental effort, remember that value 7FF8. Okay? That's a pure NaN. NaN is not a number, so when we have a decimal that cannot be represented, it will be not a number. Finally, we have integers, and as what I explained before, the upper 15 bits are set, so FFFE, and then the 32 bits, lower 32 bits are represented. little bit of more basics on how a JavaScript engine looks. A JavaScript engine generally works like this. So there's a parser that takes your JavaScript script and then reads the whole script, checks that all the tokens of your JavaScript language is correct, and then if it's correct, it will produce bytecode. Bytecode is something which is easier to understand for a JavaScript engine, and this bytecode could be, so you have a function in your JavaScript that has a bytecode. If you have an addition, it will have a certain bytecode. If you call any other kind of functionality or a global like math.async, that would be also a different bytecode. This goes down to the interpreter, and then the interpreter will have, for every bytecode that I just mentioned, will have a certain code that it knows how to run it. But in this, at this point, this is running slow, let's say, because the interpreter doesn't make any assumptions of which values you pass. Because in JavaScript, you can add two numbers, you can add an integer and a decimal, you can add an integer and undefined, you can add an integer and an object, and JavaScript has to say, OK, let me check how I do this. However, if we execute something many times and with the same values or the same types, then it will generate, on those bytecodes, it will add profiling. The profiling would be, amongst other types of things, it will add types to that bytecode. So it can generate, it can do assumptions so that it can generate, it can compile and optimize code at runtime. So while your JavaScript runs, in JavaScriptCore and the major JavaScript engines, they have compilers built inside. So your JavaScript code gets compiled, and then it also gets optimized. When this compiler generates the code, it can violate the assumptions, and then it will de-optimize the code and try to reprofile it again. In JavaScriptCore specifically, we have from left to right. So left is the slowest, and right is the fastest code running. From left to right, we have the low-level interpreter, the baseline, the DFG JIT, and the FTL JIT. We're going to focus on the DFG JIT. All of these, they use an intermediate representation. LLint and baseline, they use the bytecode, and DFG, data flow graph, they use the DFG IR, intermediate representation. FTL, faster than light, like again, Apple with the funny names, also like a web template framework. They use intermediate representation, the bare bones backend, and the assembly IR, and they all produce code. We're going to see a little bit of DFG IR later. Cool, so now we have the basics. We now make that effort for that JS value, because that's going to be important. Make that effort for that NaN. Okay. A little bit on the fuzzing and how this quest started. I like to start with fuzzing before auditing any code, because it can be running on the side, and when I audit code, then I can guide the fuzzers. And this is what it is all about, having an edge, because when you do fuzzing, and you are not in a big corporate, you don't have access to thousands of cores. So you need to have some kind of edge. And here, we are introducing to you something that we had internally for a couple of years. And it's a fuzzer that is built on top of Faceli. You don't need to reinvent the wheel. If something is really good, you just use it and then build on top of it. So Faceli was made by Samuel. That was a project here as well. And it's a fuzzer that has an intermediate language, and that's what gives it an edge against other fuzzers as well, because it can generate really good JavaScript code. It can generate syntactically correct code and then lift it to JavaScript in a very good way. And then we have that we built on top of it, defaceli. Defaceli, basically what it does, it's a very simple concept. So every time that faceli from the intermediate language lifts to JavaScript, it will lift an expression like this. And what we did just is on the lifting, we said, OK, stringify this and print it. And this is how defaceli works. We let faceli generate the new test case, and it will lift everything to those statements that I saw before. So for every JavaScript statement, it will add a print, analyzing whatever was on the content of the JavaScript statement. Then we execute two versions of the same JavaScript engine, or different JavaScript engines. We had the capability to do this, one with the just-in-time compiling enable, and another one without the just-in-time compiling enable. Then we got the output from one, the output from the other, and we compare the runs. If they differ, that means that either the interpreter or the optimizer has effed up. Okay? And if they have effed up, we can save the test case and then analyze it afterwards. After a year and something of having the facility, we saw that JIT picker appeared. And just to mention it, because it's also a really nice implementation of differential fuzzing building on top of facility. The difference that they do is that they patch the JS engine. So they have, in the tracking statements for differential fuzzing, it's built with JIT support. However, we were very intrusive because we were adding print statements, and that breaks some compiler optimizations that we could do. So how do you increase your luck in fuzzing? Now we have the edge, we have the differential fuzzing, but we needed to actually target specific things. This is how you increase your luck. So these two images, okay, one is specific to your instrumentation. So what is the code coverage that you want to apply to your fuzzing runs? And this is what kind of things do you actually want to generate. Okay. So how Facility works is that it uses the f-sanitize trace PC guard, and you can actually put allow or disallow list. So it makes no sense nowadays that you compile the entire browser or the entire application and you instrument the whole thing and let your fuzzer run against it. It's going to be slow, and you're going to hit very shallow paths, unless you're the luckiest person in the world. So what you can do with an allow list and a blacklist is just tell it, if I want to target, for example, JIT, I know that I need to run things many times so that they get compiled and optimized. So I want to just go for loops, while loops, and all of that. So with the allow list, we'll go into the JavaScriptCore code and check which are the functions that look like they will be JITed, or just go to the JIT code and say, I just want to instrument the JIT code. And in the interpreter, whatever generates for loops and all that stuff. And then in Facility, there's also, which is a really good thing that Facility has, is that you have code generators, and the code generator will generate a function, or it will generate an integer, or it will generate whatever you can think of. And you can add weights to that. So for example, if we are targeting the JIT, again, we have the for loop, for of loop, and we will increase the weights of this. So again, know your tools. This will help you increase your luck. Cool. So now we're getting to the bugs. But you thought we were done with fuzzing. You're in for a treat. So the first bug is something we found with fuzzing. And the key thing that I want you to think about this bug is that when the JIT compiling is generating code, is that it needs to use registers. But for whichever target architecture, we have a limited amount of registers. Think about that, limited amount of registers. And here we have GPR and FPR, general purpose registers and floating point registers. Think about the JS value, how we had the doubles, how we had the integers. Everything is connected. So we had that in the fuzzers, even though we were doing differential fuzzing. We had a differential test case, and that didn't work out too well. And then we had an assert, and then it hit it, and then we spent a week or so trying to do the root cause, and like we couldn't get anything. It's like, how is this happening? What is happening here? And how we can like leverage this? So we were like, OK, let's write a template for this in Facility, and just let the fuzzers run. And the fuzzers in 1 or 2 days, this is a template that, well, a very similar template to this. You can see here how in Facility, I'm calling the foreign loop and then generating more random functionality in there. It was very similar to this. And in that way, we finally got through the fuzzers only. We not only found the bug, but we also got the POC, a very close thing to the POC. And this is basically what's happening. What was happening is that the JIT compiler was generating disassembly code. And remember the registers that I talked about, that there are a limited amount of registers? So when it was generating the code, it said, OK, I ran out of registers, so I need to spill them to the stack. And that's what's happening in the push R8 and R9. Okay? So when the code that is being generated pushes something to the stack, it needs to recover it afterwards. So that's why we have the pop R8 and pop R9. However, the condition, in the initial condition, is never satisfied. So what happens if I don't execute push and push, but I pop? I will get arbitrary data from there. So from this one, what we could get, the only thing we could get, like when you see this, like, oh, the type confusion. But no, we could only get an info leak out of this. Due to time constraints, you see me that I'm speaking very fast. We cannot do a deep dive into the foreign commit, but believe me, it was very big. Cool. So, and before we go now into the second bug, a little bit of type erasing in JavaScript. So on the left, we have that we create an array buffer with 8 bytes. And on the right, you see how we will look in memory. So on the left, JavaScript, right in memory, and below, the accesses in JavaScript. So we start with an array buffer of 8 bytes. And that creates binary data in the memory of JavaScript core that we can have views with JavaScript. So we create 2 views, one as a float array and another one as a big uint64 array. Okay, so with the float64 array, I can access the same data as the big uint64 array. Remember this, because we will use this. So if we print the position 0 of F64 array, we see that very long number in the IEEE 754. And if we print the v64 array on the position 0, we see that integer, which is the representation of 0x00, E2, 01, 04, etc., etc. Okay, so we have views on binary data. Now, where are we? We fuzz, we try to build a POC, we get fuzzing, we have a POC, we have the info leak, but we are in need of a better primitive or something to support that info leak, because we have an info leak, but we need something to run code, right? We need to something further. So while looking at some code that the fuzzers were hitting on the same path, I saw something. It's like, hey, Vignesh, isn't there something like just takes a general point register and straight makes an object? And that was the day before. The next day, in our very professional chat, Vignesh goes like, Elmao, I think I found a different bug in JSC. And sure enough, he pointed to, I asked, hey, what is the vulnerability? And he said, the code that you said, what's happening there is that they don't have the check for not a number. So they are boxing things, but they are not checking for not a number.
All right, let's exploit some NaNs now. So the next bug is basically found by code auditing when we were looking at the previous bug. And we are going to call this the NaN bug just because this stems from the way in which JavaScript core is fetching NaN values. NaN is basically not a number, floating point value. So when we were looking at the previous bug, we actually came across this function. You don't have to read the code, but we came across this function. And the name of the function actually kind of tells us what the function is going to do. Let's just look at it. It's called compile get by val on a float typed array. And so what is a get by val? So in JavaScript, let's take this second line of JavaScript. We are actually accessing an element. We are fetching an element from an index in an array. And when we are going to when the JIT compiler is actually going to compile this code into assembly, this element fetch is going to be converted into a get by val opcode in DFG. And since this get by val is actually on a floating point array, we are fetching from a floating point array. This is going to be a get by val on a float typed array. And that is what our function name actually was. It was just compile get by val on float typed array. So that function was essentially going to compile this second line of code into assembly. Assembly is usually ARM64 on iOS and M1 Max. So in this function, the meat of the code is actually done by this highlighted box. Again, you don't have to look at the code, but essentially what this is doing is that it is emitting assembly code for the element fetch. So that element is fetched and saved into a register. Let's just call it result register. This will be the target architecture register on when the code is finally emitted. One thing to note here is that float64 arrays actually have raw floats. That is IEEE 754 floats. They are not JS value floats. Like how we were saying, typically when in JavaScript, everything is NaN, all the floats are NaN boxed. And in float 64 array, they are not NaN boxed. So when we load a float from a float 64 array, it's an unboxed NaN. That is what is there in the result rich. And the next job of the engine is to actually NaN box that array. And that is what this box double function is going to do. It is just going to add 2 to the power 49 to that float that we just fetched. If we just peel off a couple of abstractions from that box double function, we actually see that what it's doing is basically sub64 this trusted number, number tag from the input that we gave, the float 64 value. What is that number tag? That number tag is basically this value. The upper 16 bits are 0xFFFE and the rest of the bits are null. If you, this value, what is that value? That is value is basically the 2's complement of 2 to the power 49. So 2's complement of 2 to the power 49 is basically negative 2 to the power 49. And we are subtracting negative 2 to the power 49 from our input, which basically means that we are adding 2 to the power 49 to whatever float that we just fetched. So the interesting part here is that JavaScript core just made an assumption here. It assumed that the floating point value that we just fetched from the float 64 array is going to be within a range. Javi was talking about that in the JS value section. Floating points are usually within a range. Nowhere did JavaScript core actually check that it's actually within a range. That makes sense. That is correct, because you can't give invalid floating point array typically in JavaScript. However, Javi was also talking about something called floating point, about the typed arrays where we can actually manipulate an array buffer with a float as well as a big int. That means that if we the value in a floating point array can literally be arbitrary 64 bits, which means that whatever value we are the value that is being subtracted from the GPR, that is completely user controlled in all the bits. That means if the value that we give in the floating point array is that one on the left, that's FFFE 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. This you cannot give it from you cannot make a floating point, a valid floating point normally, but we can with typed arrays. We'll see that soon. But let's say this is the value that we give. Then what JavaScript core is going to do is that it is going to subtract the number tag from it, which is basically FFFE. So the FFFE is going to cancel itself out, and we are going to be left with only the lower 32 bits, and the upper 16 bits are all nulls now. Javi actually said that when the upper 16 bits are null, it's a pointer. So we basically converted a floating point value into a pointer. So we created a pointer out of thin air. And the assumption that we broke here was basically that JavaScript core assumed floating points are going to be within a range without making that check anywhere. And in reality, that is not true. We can actually give an arbitrary floating point value. That's an invalid, impure NaN. Because the upper bits are set, that's a NaN. But that's an impure NaN, because there is only one type of NaN in JavaScript core, which is the pure NaN. And since we can give a pure NaN, we actually break assumptions of DFG, and we arrive here at a position where we can convert a number into a pointer. So let's just look at a trigger for this in JavaScript. The path to hit this also comes from the commit that we talked about, which was about implementing a for and iterator. So on the left there, we have the trigger for this bug. First, we have the for loop, the for and iterator, where I is the iterator. After that, we have the array access that we were talking about. The arg will actually be a float 64 array. Now we are going to JIT this function. JITting a function is as simple as calling that function multiple times. So we are going to just call that function like 0x1000 times, and that's going to get JavaScript core to JIT it. Now comes the interesting part. Now we are going to we JITted that function with that fbuff. What is that fbuff? Fbuff was a float 64 array on this array buffer. And we have an alternative view on that array buffer, which is the begin 64 array. So we are going to now manipulate that underlying view with a begin 64 array. So with begin 64 array, we set the 0th element to FFFE123 with the malicious value. And since we set the begin 64, the 0th element, the fbuff 0th element is also set to that same value. Now we call that function again. This time, this is the code that is going to be executed is the assembly code, because this function is probably JITted by the time we get here. because of the for loop. And when we go inside that function, we eventually hit that highlighted code, and I is eventually 0 at some point. That means we are going to fetch the malicious value there, which is 0xFFFE1234567 The bug is going to get triggered, the FFFE is going to go, out is going to be a random arbitrary a pointer that we control, which is 1234567 That is going to be saved to the property x, and outside the function we are going to access that property x, and here we are going to crash, because this is now JavaScript core is now trying to access a object pointer that is invalid, because this is now completely controlled by us as the attacker, and it is going to crash with an invalid memory access.
Okay. Testing. Hello, hello. Hello, hello. Okay, good. What a mouthful, right? Like he said, we can create pointers out of thin air. So we can create JS values to whichever object. And now you have to think. We had two bugs. We have an infolic, and we have an arbitrary dereference. So with those two things, we have the infolic, the arbitrary dereference, very good primitives to have remote code execution. Unless Apple patches it in like 1 month. So where are we now? We did the fuzzing. We have the infolic that is patched. We have now the arbitrary dereference, and we got the remote code execution. We are very happy at this point. It's like, no. So then we go to the fuzzing and more auditing. So now we are retargeting the fuzzers, trying to look at different avenues, like improving the differential fuzzing. And this red dot is where we are. This bug is the one I told you. It has nothing to do with the with exploitation, but it presents an important part in our research. It basically was a differential test case, and we spent another good week or two just looking at what was happening under the hood, because basically in the switch case, one of the without the JIT, it was doing it properly, and then with the JIT, it was just jumping to the other condition, and we were like, "What's happening here?" Basically, what was happening is that it was trying to make a comparison, a strict equal comparison between the switch case and a dead node. So the compiler thought that this variable died, and nobody was using it, incorrectly generating the assembly code. However, when we were doing the root cause analysis, Vignesh had a fantastic breakthrough, and he thought something really, really good that he's going to show you now.
Right, so when we were doing the analysis for that bug, we actually came across this DFGIR. The top 2 lines are actually DFGIR, and the assembly that you see here is the assembly that is emitted corresponding to that IR by the DFG compiler. So the ones highlighted in black and gold are basically the name of the DFG opcode. It's called compare strict EQ. Now, what is this compare strict EQ? Well, compare strict EQ is basically the strict equality or the triple equal to operator. If you don't know the triple equal to operator, for the purpose of this talk, you can just think of it as the double equal to operator in any language. You have a left-hand side or an LHS and a right-hand side or an RHS, and it will compare LHS and RHS, and it will return whether they are equal or not. So let's get back to the DFGIR. And in the DFGIR, so DFG is a compiler, and in order to compile code, it needs type. However, JavaScript core does not have types. Like Javi was saying before, JavaScript core does have profiling, and DFG gets profiled types. So DFG makes assumptions on types of LHS and RHS. So in this case, what this highlighted box is telling us is basically that the LHS is untyped. So DFG does not actually need the type of the LHS. However, the RHS is speculated to be an object. DFG thinks that RHS is going to be an object, a JavaScript object. And if the compiler makes an assumption, it has to validate that assumption. And it does so just below. This compare instruction is basically validating that assumption that that thing, RHS is an object, 0x17 is the tag for an object, and RAX is basically RHS. If that comparison passes, what we are going to do here is that we are going to basically compare LHS and RHS. LHS is in RDX, RHS is in RAX. This is a raw pointer comparison because this is literally a x86 compare instruction. So we are going to just compare both LHS and RHS, raw pointer comparison. And the result is going to be sent back to JavaScript. We are going to have the result for this. The interesting part is that we did check the type for the RHS. However, LHS is not checked, and that makes sense because LHS need not be checked. LHS does not have a type, no assumption is made. However, what if LHS is an invalid pointer here? If LHS is an invalid pointer and RHS is a valid pointer, then we are basically comparing a valid pointer against an invalid pointer here. And the result is returned back to us. And nothing bad happens if the invalid pointer is never dereference. So nothing bad happens. So we have a mechanism here where we can compare a valid pointer against an invalid pointer and get the result. So all this is a perfect setup for a brute force. So just like we basically needed a technique, and just like Asterix is hitting that legendary with a amphora of brute wine, we are going to hit Webkit with brute force. So let's see how brute force can actually be used in JavaScript exploitation. Let's quickly look at this POC, and this is basically what we just talked about, that triple equal to check. We have the check is on the .x property just to satisfy some JIT shenanigans. And then we JIT compile the compare function here. Again, just one thing to note here is that if you notice, A2 is an object. So we are basically training the JIT compiler by saying that RHS, take the type of RHS to be an object. Once we train the JIT compiler, we need a valid object. We need LHS can be, from the brute force technique, LHS can be an invalid, RHS can be valid. So we need a valid object in RHS. So this is the object that we are going to leak. We just picked a random one. We just want an address. So we just picked a random object to leak. Then we are going to iterate over the entire address space. We'll get back to this later. This is the starting of the brute force. After that, remember that the NaN bug actually allows us to create a pointer from a number. So our number is basically the iteration count I. We are going to convert the current iteration count into a pointer here. And after that, we are going to pass the invalid pointer. This is going to change with each iteration to the valid pointer. LHS, RHS, this is compared, and the result that we get will actually tell us whether they are equal or not. So if they are not equal, that means we guessed it wrong, just continue. However, if they are equal, that means we guessed it right, and now we are going to, and we have the address. We have the address of the object. So how feasible is this actually? Like, is this going to, like, that this loop, does this hold for 64 bits? JavaScript heap pointers on macOS and iOS were actually less than 40 bits, and but even with 40 bits, the brute force still took over 2 hours, and that is not really feasible for a browser exploit. So we need to optimize that brute force. So we set out thinking how to optimize this, and the first breakthrough we had was that when we saw that, wait, pointers are actually multiples of 8. You don't have, in JavaScript core, you don't have a pointer that is like ending in 1 or 2 or something. So our loop count can actually iterate in multiples of 8, which is a straight up 8x performance benefit. From 2 hours, we can literally go into 15 minutes. But even 15 minutes is far too much for browser exploit. So we need to optimize this further. So going down the same path, we actually just thought what would happen if we have more bits that are constant. Well, it turns out that Safari has something called web workers. And web workers are basically, you can think of them as threads on JavaScript. And they can execute a JavaScript script on a different thread. The interesting part about web workers was that web workers have isolated heap contexts, and when the first object that is allocated in a web worker script is actually aligned to a page start. And if an object is aligned to a page start, it will have at least the lowest 12 least significant bits as set to null. If we basically here what we have is that we found a method where we can have an object whose address will have the lowest 12 least significant bits to set to null, which means that we can actually do the loop count iteration iterations of 0x1000, which is a 0x1000x performance benefit, and now our brute force takes less than 3 seconds. And this was perfect for exploitation. So the only difference is that I plus became now 0x1000, the rest is the same. So basically with that, we have a way to bypass ASLR by brute force. We have a way to craft arbitrary pointers out of thin air with the NaN bug. Now putting together both of them together can actually give us an RC. We have a fake object from the bug. What is a fake object? Fake object is basically the ability to convert C pointers into JavaScript references. And that is what the NaN bug actually gave us. We have a partial ADDR from the brute force. And what is an ADDR of? It's basically the ability to leak the address of any JavaScript object. We can't leak any object, but we can leak one object. With some simple heap manipulation, it's actually trivial to make this into a full ADDR of primitive. And once we have the fake object and the ADDR of, we can actually get arbitrary read-write in the renderer context. It's with some effort. This has already been documented well by other researchers in CV write-ups as well as CTF write-ups. So we are not going to repeat that here. So let's look at a demo of the brute force here.
OK. So something to say about this. You see that this is a comparison that is being made inside JavaScriptCore. And we are using it just with another bug. But what's happening here, that this is not a bug. It's a feature. So there's nothing to fix here. That's how JavaScriptCore works. Cool, let's go into the demo. Let's see,
It's not showing.
yeah, now it's showing. OK. So what's going to happen here is that we are going to get the ADDR of an object. We're going to corrupt the data pointer and point it to wherever we want, and we're going to write whatever we want to another place. What you're going to see on screen, hopefully, is the brute force happening very, very quickly. And then at the end, let me show you in code. Back to. Yeah. So what's going to happen here is that we're going to iterate, like Vignesh said, throughout all of those values. In Intel, it's also a fixed value. Well, I haven't rebooted the machine, but I managed to fix some values, and it takes well below 3 seconds. And what we are trying here is to try to find that object that we want to corrupt. OK? And then if everything works well, we should have that we corrupt x1, that is 0x1337, and it should show pwn. If it shows pwn, we were lucky. Yeah. So let's see. Webkit build. I haven't sacrificed any codes to the demo gods. Release, bin, see, and then back. So it should happen very fast. The brute force is fast, right?
This is on Linux, by the way. So.
Nice. OK, so we got one. Let's see. How many hackers did it get?
That was on Linux. On Mac, it would be faster than this.
Yeah. Cool. And again, remember that JS value, that NaN. This is what they're doing here. They're purifying the NaN and making it 7FFF8. That's what pNaN is. So when we have a purified NaN, there's no overflow that can happen when we add the numbers. It was a very simple fix, but a very powerful primitive. Cool. So if you think that at this point we have nice code execution in the renderer, no way, Jose. We have that we will need to bypass PAC and APRR. So PAC has been talking in a previous talk. Basically, it's signing pointers. You need to bypass it somehow. And there's also APRR. So you cannot write a page that is write and execute. So you need to find also a way to bypass, plus the sandbox, plus all this stuff. But for those non-believers, here's the exploit working on iOS. And here is us reading the etc passwd file on an iOS device. This all has been fixed, OK? Cool. So some conclusions. I don't want to eat into your lunchtime. So again, the same premises as Ian. A huge commit, thousands and thousands of lines of code that one would think it was tested. And when we saw it, it's like, let's try if it's tested. You saw here from the many bugs, all happening from the same commit, that it wasn't that, that well tested, or at least not the places that we were looking at. They fixed it afterwards. Fuzzing and code auditing, they go hand in hand. So fuzzing should be something that you should have in your tool set while you're also doing source code auditing. The more you know about the code, the more you can fuzz. And the browser landscape is ever-changing. So you saw that in 1 month they patched it, and the most that it took these bugs to be fixed, it was in less than a year. In fact, when you see any of the Git repositories of the major browsers, they have from 5 to 10 commits a day. It's crazy, even on holidays and sometimes on weekends. Cool, so I don't think we have time for any questions, and I don't think we're going to be around because we're going to go for lunch, right? So thank you very much.